Okay, so we're starting our discussion of forces. And a force, as I suppose you can read there, is basically a push or a pull. And all forces, as it turns out, are what are referred to as field forces. In other words, there is a field that causes a force on bits of matter and other things that are within that field. Okay, so for example, if you have something that has mass, it creates a gravitational field around it, and thus other things that have mass feel a force of gravity when they're near that object. Okay? Now, for our purposes in mechanics, we can basically categorize forces in a little bit more of an intuitive way, maybe, and that is in terms of contact forces. So things where you must be in contact with another object to exert that force, and forces that act at a distance, all right? And the only force that we're going to be considering in this class that acts at a distance is gravity. Okay? There are certainly other ones. In fact, the contact forces themselves are a result of electric and magnetic fields, which arise from electric charge. So here we're looking at two positive charges and a map of the electric field around those two positive charges, which gives you an indication of the direction that other charges would feel an electric force within that electric field. And over here on the right, and you can probably tell from the label here that I've rotated this, but this is a picture of the, so not a photograph, okay? So this is sort of an illustration, but the sun's magnetic field as based on instrumentation, taking a look at the sun's magnetic field. You see it's very complicated. This represents the magnetic field around the sun, and thus dictates the forces that moving charges would feel if they were in proximity to the sun. Okay, so those fields, electric and magnetic, are things that can cause forces at a distance. But in terms of what's causing the contact forces that we feel when we put our fist on the table or touch your Apple Pencil to the surface of your iPad like I'm doing now, or put your pencil to paper, or catch a ball, or open a door, or whatever, all those contact forces that we feel are a result of a colossal number of interactions between electric and magnetic fields, between all of the atoms making up that matter that we're in contact with. Because as you've probably heard, matter is mostly empty space, and so it doesn't really make sense that we're somehow colliding with the bits and pieces of matter. If it was all mostly empty space, then we'd expect to somehow pass straight through, and yet we don't. And that's because of these forces, and admittedly they're forces at a distance over these tiny little atomic scales, but they build up to just give us a feel of actually being in contact with something, okay? So contact forces require us to actually be in contact with the object, which means that since gravity is our only force at a distance that we're considering, if you aren't in contact with something, whether it's the air, if we start talking about drag with our projectiles, or the ground, or somebody's hand, then you're not going to feel that force. And when you're talking about a projectile, and here's a diagram over here of a projectile's trajectory and all the horizontal and vertical bits of its velocity that I've borrowed from somewhere, okay? The only force acting on that projectile, right, in our ideal projectile model, is the gravitational force, which causes that constant gravitational acceleration when we're near the surface of the Earth. Okay? So gravitational force, our only force at a distance. Now, there are other field forces. There are 5 fundamental forces. You could make an argument that since some of them have been unified under a single theoretical framework, like the electroweak encompasses the electromagnetic force and the weak nuclear force, right, and field. So we're seeing that here, an example of that here. But there are basically 5 fundamental fields and thus forces. So there's gravity and there's electricity. So electric forces and fields. There's magnetic forces and fields. There's weak nuclear fields, which govern interactions like this one, where a free neutron, so not bound into an atomic nucleus, for instance, one of its quarks here decays from a down quark to an up quark, which turns it into a proton and a W minus boson, which then further decays into an electron, so that's this thing right here, and an antineutrino over here. Okay, you don't need to know any of that. This is just, fleshing things out here, so we can talk generally about forces. Okay, but weak nuclear fields govern these sort of decays and other things like radioactive decay and stuff like that. You'll see weak nuclear fields come into play, and weak nuclear forces come into play. Strong nuclear forces are perhaps a little more intuitive, a little more concrete. That's what's holding atomic nuclei together, for one example. Okay, because if you know anything about electric forces, you would expect all these little positively charged protons to be repelling one another because they're all like charges. And that's certainly happening, okay? But on the atomic nucleus scale, like this 10 to the negative, 14th, 15th meters, many zeros and then a 1 on that scale, there is a strong nuclear force which causes a very strong attractive force between protons and neutrons. And when you have large nuclei like this one, where there's lots of protons and neutrons, the strong nuclear field, and that's the strong nuclear forces on all of these nucleons, the particles in the nucleus, like neutrons and protons, are such that they counterbalance the repulsive electric forces that the protons are feeling that are trying to repel them apart. It's part of the reason why there's an upper limit on how big nuclei can get, because eventually the nuclei get so big that the strong nuclear forces sort of start dropping off in terms of their magnitude, and the electric repulsive forces start getting quite large, and the nucleus essentially tears itself apart, or at least becomes far less stable than it would otherwise be. Okay? But this is the first and last time we'll see weak and strong nuclear fields. They're certainly very important. They govern all of these processes that go on in nature and make sure that our lives function the way that we expect them to. Strong nuclear fields in particular. We wouldn't have our atoms if we didn't have that. But we won't have it enter into our calculations. Okay? So for us, contact forces and forces at a distance. And the one example of force at a distance for us is going to be gravity. Okay. Though in your second semester of physics, or the equivalent thereof, we will talk about electric and magnetic fields. Okay. Now, in this video, I wanted to at least lay out the first of Newton's laws, and maybe I'll split Newton's second law and Newton's third law off into a separate video. We'll see sort of how we're doing on time here. But let's introduce Newton's laws of motion. There are 3, and Sir Isaac Newton, introduced them in the 17th century, and they've definitely stood the test of time in terms of describing the motion of objects that we can see and touch directly. Newton's laws can be violated, but only in contexts that we essentially won't study here in mechanics. So we can take them essentially as gospel, and we see the results of them all around us every day. So first, the first law, of course. And of course, the first law is first. So an object moves with a velocity that is constant in magnitude and direction unless a non-zero net force acts upon it. And that can be any velocity. That can be a zero velocity. That can be a positive velocity, a negative velocity, up, down, left, right, north, south, east, west, whatever, okay? But if you don't have a non-zero net force acting upon the object, well, then it just keeps going. Now, we're not really familiar with objects that just keep going forever here on the surface of the Earth, right? That would be a very strange thing. We have things that maybe come close if you put if you think about like an air hockey table and you put a puck on there and you give it a little push, then it will go and bounce and sort of keep going in one direction until it hits the wall pretty readily, right? And that's because friction, these little forces that it feels because it's in contact with the air molecules that are blowing up from the air hockey table. Those tiny little forces are enough to eventually bring it to a halt, even if it weren't to hit a wall, for instance. Okay, and so no, we generally don't see examples of things just getting, given a push and then getting a velocity from that push and then just keeping that velocity for all time, right? There's always these little forces, even if they're very slight, that tend to bring it to a halt or bend its trajectory or whatever it happens to be. But the first law, there's a couple things that we want to think about there. One, it's often stated in terms of the law of inertia, the idea that when something like this object has mass, so some number of kilograms of mass, then it has a certain amount of inertia, and it has a tendency to stay in motion if it's in motion, or stay not moving if it's not moving, and you have to apply a non-zero net force to it to get it to change that behavior. Even if you go to outer space, take a diagram of Voyager 1 here with some velocity that it's because we gave it a great big kick when we launched it from Earth so long ago, back in the 70s. And once it's away from Earth, we might expect, its velocity is, might consider it sort of a perfect example to illustrate the first law, right? We've given it this huge kick, so it accelerates from 0 on the launch pad up through the atmosphere into outer space where nothing is touching it, and so it should just have sort of a constant velocity, right? If the first law is true. And the first law certainly is true, but not even the Voyager 1 is free of external forces or non-zero net forces on it. So here's a little map of both Voyagers' journeys through the solar system, and you can see that their path is not just a straight line velocity in a particular direction. The gravity of the sun, the gravity of Jupiter and Saturn and all these planets that they cruised by and took pictures of and measurements of, have affected their trajectories a lot, right? There's nowhere close to a straight line. Though you will notice that as they get farther and farther out, and they're farther from the sun, they're farther from all of these other bodies, and Voyager 2 off in this direction, and Voyager 1 off in this direction, their trajectories do start straightening out, and they are beyond the edges of our solar system at this point, and perhaps won't encounter much else to change their velocities while they're out there, okay? Now, I've posted a companion video for this. It's a variation on the old tablecloth trick where if you're abrupt enough, you can pull a tablecloth from underneath, a set of china and some nice flowers on a table and leave everything more or less undisturbed, and there you are standing with the cloth if you're good enough. And the idea, the root of that is that all the objects on the table do have a certain amount of inertia associated with their mass. And so if you have a nice smooth tablecloth and you abruptly apply this little force that jerks that tablecloth out from under those things with so much inertia, then you actually don't cause those objects to experience much of a net force, and thus their velocity, or rather their lack of velocity, also doesn't change much. It's not a perfect example. Oh, there's my toddler at my door. So perhaps that's about the time to wrap up this video. We've talked a little bit about forces in general and the first law, and we'll be back soon to talk about the second law, some consequences of the first law, and the third law of motion for Newton's laws. So I will talk to you then.